Hello, today we're continuing in our A-level physics revision series looking at wave-particle duality. This all arises from a debate which took place in the 17th century between Newton, who was British, and Huygens, who was Dutch. They were both physicists. Now, Newton said of light that light was made of corpuscles or particles. That, he suggested, was the reason why when you fired light at a mirror, this is a mirror, it would reflect or rebound, just as a ball hitting a wall would rebound. So the corpuscles or particles of light rebound when they hit a mirror. Huygens, on the other hand, took the view that light was made of waves. And he said that every point on a wavefront is a point source of a secondary wave. So if you have waves coming along like this in this direction, then he said every single point on this wavefront is a source of light. In other words, they all have ripples, rather like every single point you throw a stone in a pond, and every single point generates ripples. And all of those ripples combined produce a new wavefront. And that, he said, is how wavefronts progress, by having each point being the source of a secondary wave. Now, most people sided with Newton because he seemed to be right on most things, but it was only in the 18th century that Young did the double slit experiment to settle the argument. The double slit experiment has been described in another video, and I refer you to that for the detail. But basically what Young did was to take waves which he directed at a double slit, separated by a distance d. D is the distance between the slits. And he looked to see what he got on a screen some distance d away. And he found that he got a fringe pattern of light and dark spaces. And you'll need to see another video, which is cross-referenced here, to see how we derive the equation n lambda equals d sine theta, where n is any integer number, lambda is the wavelength of the light, d is the distance between the slits, and theta is the angle to the first fringe. And then you can have fringes all the way along, and theta will be different for different values of n. So for the first fringe, when n is 1, theta is this angle. When n is 2, theta is that angle. When n is 3, theta is that angle. And each of these points on the screen represent a light fringe. And what Young said was that this showed that light was capable of interference, because you only get fringes through interference, and only waves can interfere. Therefore, said Young, Huygens was right, light is made up of waves and not out of particles, as Newton had suggested. But in 1887 an effect was observed which was to put everything back into the melting pot. The effect was called the photoelectric effect. And basically what was observed was if you took a metal, here's a metal, and you shine light on it, there's the light being shone on it, you will see electrons coming off of it. But only if the light has a certain frequency. In fact, this usually has to be ultraviolet light, otherwise it won't work. It has to have a significant frequency. If you go below that frequency, you don't get any electrons. And if you shine light of varying frequencies on the metal and measure the kinetic energy of the electrons that emerge, and then plot kinetic energy against the frequency of the light that's coming in, the frequency of the incoming light, what you find is that you get no electrons at all until you get to a threshold frequency F0. And then the kinetic energy, the maximum kinetic energy of the electrons, increases linearly, straight line, with increasing frequency. Now a straight line obeys a simple equation, and that is that Ke equals a constant, which I'm going to call h, I'll explain why in a moment, times the frequency, minus another constant, which I'm going to call phi, and I'll explain why in a moment. What does this mean? It means that the kinetic energy is directly proportional to the frequency, and the gradient of the line, the gradient, is h. It also means that when the kinetic energy is 0, hf equals phi. And that arises when f equals f0. So what we're really saying is that phi equals hf0, because that's the frequency when the kinetic energy is 0. Now if you measure the gradient of this line, you will get what is called Planck's constant, that's h, and its value is 6.63 times 10 to the minus 34 joule seconds. Not joules per second, but joule seconds. That, you'll notice, is a very small amount. 10 to the minus 34 is very, very small. Now, it was left to Einstein, who else, to explain what all this meant. And he explained it like this. He said, actually, light is made of particles. He called those particles photons. And what he said was that every photon of light contains a packet of energy, and that energy is equal to Planck's constant times the frequency of the light. So one of these times the frequency of the light, and that's a little packet of energy. And what he says is that the photon comes into an atom where there is an electron, and it hits the electron, and it transfers all its energy to the electron. And if it gives that electron enough energy, it can kick the electron out of the atom. But if the photon doesn't have enough energy, then it can't kick the electron out. Somehow the electron must be bound with a certain amount of energy in this atom, and only if this photon has enough energy can it kick the electron out. And that, he said, is what is happening here. In this region here, where you've got no electrons emerging, it's because the photons don't have enough energy. But once you pass the energy threshold, then you've got enough energy to kick the electron out, and more energy besides, which is why the electrons can have, as it were, a surplus kinetic energy as they come out. And Einstein said that this value phi is what's called the work function, or the binding energy, or the energy that you need to kick an electron out of the atom. So essentially Einstein says a photon of energy of HF comes in, it transfers all that energy to the electron needs phi in order to get out of the atom, and then when it's got out of the atom it will have the incoming energy HF minus phi, the energy it needed to get out of the atom, as residual kinetic energy. So the maximum kinetic energy of an electron, says Einstein, is equal to HF, the energy coming in, minus phi, the energy required to get out of the atom. That's the maximum kinetic energy. And that's what gave rise to the first idea of wave-particle duality. The light was a wave because it gives interference patterns, and only waves can interfere with one another. But it's also a particle because it is capable of coming in, transferring energy to an electron, and kicking the electron out of the atom. So light behaves both as a particle and as a wave. Now it was de Broglie who in the mid-1920s put this idea forward. He said, if light, which we had always thought of as a wave, can now also be regarded as a particle, is it possible that electrons, which we'd always regarded as particles, might possibly also be waves? And this in essence is the little bit of mathematics that de Broglie did to postulate that an electron might behave like a wave. He said, let's start with Einstein's famous equation, E equals mc squared. And I want to know what the momentum of an incoming photon might be. Well, momentum is traditionally mass times velocity, but the point about Einstein's photons was that they didn't have any mass. They had energy, but they didn't have mass. So you're rather stuck. If the mass is zero, that suggests that the momentum is zero. Well, de Broglie gets around that by saying that the mass is kind of equal to E over c squared from this equation. So now if you want momentum, mv, that equals m, which is E over c squared, times the velocity, which for light, of course, is c. And that equals E over c. So, de Broglie says, the momentum of a photon is equal to E over c. But E, we already know, is hf. That's what Einstein said. The energy of a photon, a packet of energy, is Planck's constant times the frequency of the radiation. So that equals hf over c. But we know that c and f are related and that c over f is lambda. So this is now simply h over lambda. So de Broglie says the momentum of a photon is equal to Planck's constant divided by the wavelength of the light. But this is the point where he took a few liberties. All of this is true for a photon, for light. What de Broglie postulated was perhaps it's also true for an electron. And if the momentum is equal to h over lambda, then it must follow that lambda equals h over p. And in the case of an electron genuinely does have mass. And so lambda equals h over p, which is mv. And so you've got the situation now that an electron moving at velocity v has a wavelength. Now, of course, that was taking liberties and could have been shown to be entirely wrong. But in fact, it was Davison and Germer in 1927 who essentially repeated Young's double-slit experiment, but using electrons. And the way they did it was they took a beam of electrons and they couldn't put it through a double slit. So what they simply did was to put it through a crystal. And essentially, the slits of Young's double-slit experiment were created by the gaps between the atoms. And what did they notice on the screen? They got exactly the same thing as Young has observed, a fringe pattern. And that meant that the electrons were interfering as waves as they went through the crystal. And so de Broglie's postulate had been proved to be true, that electrons behave both as particles, but they also behave as waves. And you'll see that if the wavelength of an electron is given by Planck's constant divided by mv, then if v is small, lambda will be large. If v is large, lambda will be small. But it's all governed by Planck's constant, which itself is a very small amount. Now, we have shown in the video on electric fields that the energy of a charged particle, which is being accelerated in an electric field, is equal to the charge on the particle times the voltage between the plates. So, for example, if you have a positive charge plate and a negative charge plate here, there will be an electric field in that direction. And if you put a charged particle of charge q, it will accelerate in that direction, if it's positively charged, towards the negatively charged plate, and the energy is equal to the charge on the particle times whatever the potential difference is between the plates. So it's Q times V. In the case of an electron, the charge on an electron is given by E. E is, of course, 1.6 times 10 to the minus 19 coulombs. But the energy of an electron can also be given by half mv squared. That's the kinetic energy. And so this and this must equate. And that gives us that EV equals half mv squared. And just to confirm, this is V, capital V for voltage, this is small v for velocity. And that means we can say that V squared, just rearranging this equation, V squared equals 2E capital V divided by m. So V is equal to the square root of 2E capital V over m. Now, we've just shown that lambda, the wavelength of the electron, is Planck's constant divided by mv. If we substitute v in here, we get that lambda equals h over m times the square root of m over 2e v. And if you take that m inside as m squared, then that m will cancel out and you are left with h divided by the square root of 2mev, where v is a capital V for voltage. So this relates the wavelength of the electron to Planck's constant, its mass, its charge, and the voltage between the plates. Now the question arises, if an electron as a particle can have a wavelength, can any particle, or indeed any object, have a wavelength? Well, in theory, yes. You and I have wavelengths, but in practice, it's impossible to detect them. And why is that? Well, let's have a look. Lambda equals h over mv. Let's take an object like a ball and let's keep the maths simple. Let's make the mass 1 kilogram and let's have the velocity as 1 meter per second. Not unreasonable. So we've got 1 times 1. That means that lambda equals h over 1. And what is h? It's 10 to the minus 34. So the wavelength would be 10 to the minus 34 meters. And that's immeasurable. You would never be able to measure a wavelength as small as that. So for all practical purposes, the wavelengths that you and I have are immeasurable, and we do not see ourselves as waves. We see ourselves only as solid objects. Slit, separated by a distance d. D is the distance between the slits. And he looked to see what he got on a screen some distance d away. And he found that he got a fringe pattern of light and dark spaces. And you'll need to see another video, which is cross-referenced here, to see how we derive the equation n lambda equals d sine. So if you have waves coming along like this in this direction, then he said every single point on this wavefront is a source of light. In other words, they all have ripples, rather like every single point you throw a stone in a pond and every single point generates ripples. And all of those ripples combined produce a new wavefront. And that, he said, is how wavefronts progress, by having each point being the source of a secondary wave. Now, most people sided with Newton because he seemed to be right on most things, but it was only in the 18th century that Young did the double slit experiment to settle the argument. The double slit experiment has been described in another video, and I refer you to that for the detail. But basically what Young did was to take waves which he directed at a double... Hello, today we're continuing in our A-level physics revision series looking at wave-particle duality. This all arises from a debate which took place in the 17th century between Newton, who was British, and Huygens, who was Dutch. They were both physicists. Now, Newton said of light that light was made of corpuscles or particles. That, he suggested, was the reason why when you fired light at a mirror, this is a mirror, it would reflect or rebound, just as a ball hitting a wall would rebound. So the corpuscles or particles of light rebound when they hit a mirror. Huygens, on the other hand, took the view that light was made of waves, and he said that every point on a wavefront is a point source of a secondary wave,